So hello everyone, my name is Shahin. As I said, I'm a PhD student in computing science at VQA, and I'm a member of Explainability AI Lab led by Professor Randy and Professor Osman. Today I will present my recent work entitled as Explaining Autonomous Driving Actions with Visual Question Answer. And in this project, I worked with Mohamed Salameh from Harvard, Canada, Osman Babike, and this Professor. So this presentation is primarily based on our recent paper, which has been accepted to the International Conference on Intelligent Transportation Systems, which will be held in Spain, and I will present it in Spain in September. Here is a brief agenda of my talk. I will first talk about a brief overview of autonomous driving. Then I will talk about the need for explainability in the context of autonomous driving. Then I will say what's existing approach for explaining autonomous driving actions, and final our work, which are our experimental design, results of our experiments, and conclusions and the future directions within this work. So what's an autonomous driving and how decisions are made in autonomous driving in real time? Well, decision-making in autonomous driving consists of 4 interrelated kind of operations. These are kind of perception, localization, planning, and control. Perception is an ability of a self-driving vehicle to sense its operational environment. And localization is capability to understand position in its driving area. Then planning is kind of finding a route from initial point to final destination along its trip. And finally, control is kind of proper execution of chosen actions by a self-driving vehicle. And by this way, an autonomous car can steer, adjust its speed accordingly, stay in a lane, and keep a distance with stationary and dynamic objects around it. So this is kind of high-level picture of real-time decision-making by an autonomous car. What is the state of the art in autonomous driving in terms of their automation capability? Well, SAE International has defined 6 levels of automation, which are from level 0 to level 5. In level 0, there is no driving automation at all. In level 1, autonomous cars are kind of equipped with adaptive cruise control. In level 2, they have advanced driving assistance systems. And finally, in higher levels, they have obstacle and object detection. And in level 4, they have near full automation in a geotransit area, where Alphabet Swim claims that they have reached the level 4, but it's still a little bit skeptical. And finally, it means that everything is automated here, and no human supervision is required at all. This seems somehow ambitious and not reachable in my point, but yeah, let us see. Okay, now that we understand what's automation, autonomous driving, but why do we need explainability in the context of autonomous driving? Well, there are several reasons for this. First of all, psychological perspective. Traffic accidents and the safety concerns with the presence of autonomous cars. For example, here I have shown a picture. As you can see, a Tesla sedan here hits a parked vehicle in the curb in Laguna Beach, California in 2018. So safety concern is kind of one of the biggest kind of problem in autonomous driving, which is about psychological perspective. Then the second one is socio-technical perspective. Means that design, development, and the deployment of autonomous cars should be human-centered. So it should reflect the end user's needs, and it should also kind of take end users' opinions and expectation in design, development, and deployment process. And then philosophical perspective. From the philosophical perspective, it means that explainable AI decisions can provide descriptive information about the causality of real-time actions. For example, if you look at this picture I have put, an autonomous car stops in a pedestrian crossing, and it provides information in natural language, like stop it because waiting for the pedestrian's crossing. So it's an information kind of given to bystanders in the traffic scene. So this kind of philosophical perspective. And finally, the fourth perspective is kind of legal perspective, where explainable AI is toward becoming a concrete legal requirement. So European Union has a specific regulation initiated in 2018, which is called General Data Protection Regulation. It means that AI systems should be safe, and on top of being safe, they should also provide some kind of explanations on how it makes decisions. So this is kind of legal expectations, and it kind of constitutes a legal perspective in the context of autonomous driving.
Could you minimize the Thank you.
So these four reasons show why we need explainability in autonomous driving. So if we summarize explainable autonomous driving, we can say that an explainable autonomous driving system should ensure an acceptable level of safety on its decisions, and it should also provide explanations on real-time decisions, especially when these decisions are kind of critical. And of course, it should also obey all traffic rules established by the regulators.
Before you talked about this, you talked about perception, you talked about planning, control, localization. Are these explanations on one particular side of this, or all the four?
All the four. So all the four kind of constitute kind of real kind of concrete action, and my research kind of tried to explain end result action.
So it's not just the control.
Yeah, exactly.
Philosophically, if you think about those four and their integration, you want to be able to debug them. That's what this is about, really.
Yeah, exactly. Okay, now we understand, why we need explanations in the context of autonomous driving. But what are some kind of state-of-the-art approach to explaining autonomous driving actions? Well, currently in autonomous driving community, researchers have tried several ways. These are mainly visual explanations, textual explanations, feature importance scores, and the multimodal explanations. So visual explanations, as seen from its name, kind of provide kind of some explanation in visual format, which can be heat maps, class activation maps, and interactive visualizations. Then textual explanations aim to deliver information using natural language. It could be kind of information about scene descriptions, causality of actions, and kind of some information about temporal scene. So this kind of constitutes textual explanations. Then future importance scores are kind of quantitative metrics, which shows, for example, how much each parameter kind of contributed to model's prediction. And finally, multimodal explanations, which could be kind of combination of several explanations, such as a vibration, some haptic feedbacks, and the tactile sensations. So these are kind of general explanation provision methods in the context of autonomous driving.
Question: so you say tactile sensations, that is the output, that the way in which you convey an explanation by something vibrating?
Yeah, I mean, autonomous car actually, for example, let us say, for example, when there is a barrier or obstacle very close to the car, it can provide such kind of sensation, such as vibration, or I don't know, some kind of.
This is the output. This is the way in which the explanation is conveyed.
Yeah, exactly. Yeah, exactly. Explanations can be conveyed in this way. Yeah.
The autonomous driving group at VQA in Germany has one aspect and one set of frameworks for experiment is to decide how to use feedback to drivers to say, oh my God, the geolocation device just broke down, take over now. And how to convey that is done in lots of different ways. For example,
You get an actor that conveys information also. Go on.
Yeah, basically it also,
hopefully to avoid the pits.
yeah, especially, yeah, I mean, such kind of explanation, let us say, delivered using tactile sensations or haptic feedbacks can help to transfer control from, let us say, autonomous car to backup driver if there is a kind of real danger. And okay, now let us talk about our work, which is kind of explaining autonomous driving actions with visual question answering. So in this work, the core idea is that we control actions of self-driving vehicle using reinforcement learning, and then we incorporate visual question answering approach to explain such actions. And I will go a little bit ahead and give an example from our kind of results. Here, for example, we have a driving scene generated by an RL agent, right? So this image. And here we have kind of visual question answering part here. So we have an image, we have a question about this image, about an action in this image. For example, in this image, when we ask, why is the car turning to the right? Visual question answering system intends kind of to predict and correct answer for such questions about an action in such kind of driving scene. So it has kind of, here I have shown top 5 predictions, and the prediction with highest kind of softmax probability score becomes kind of the main prediction of a VQA system. So this is kind of high level idea of our framework. And our framework in general consists of 3 primary steps. These are kind of data collection, data annotation, and the question answering parts. So data collection is done by using reinforcement learning, and data annotation is performed by humans, by us. And finally, question answering as a framework, we use visual question answering approach. So I will talk about the details in upcoming slides. And this is kind of high level kind of description of our framework again. So here it is, here kind of we show deep reinforcement learning agent which generates kind of driving video from a self-driving vehicle's field of view. Then once we have driving video, we convert it to kind of image sequences uniformly. Then for generated image, we ask a question. For example, let us say this is going straight action, right? Why is the car going straight? Then we have kind of question answering framework here. I will explain this part later. But then model eventually predicts the correct answer because the road is clear. So based on this image, we have this question: why is the car going straight? And our VQA framework predicts the correct answer as because the road is clear.
So, are you telling me that the explanation is not, it does not depend on what the policy that was actually learned?
Yeah, exactly. Actually, this is kind of post hoc explanation approach. I will describe this more, but here our kind of explanation approach is independent of RL agents' decisions. So we firstly kind of generate also data which reflects RL agents' operation in car lab. Then we try to use external tool to explain such actions. And I will explain its kind of pros and the cons in upcoming slides.
So the question is good. Answers to questions arising from the visual inspection of the sensor fusion. But you can imagine the explanations being used by an engineer in a loop to debug policies and add influence on the policies in a more dynamic way, for sure.
And thinking about the European Union concerns, would that satisfy it?
Very hard to know that. Lots of AI experts and about a dozen lawyers would have to be consulted first.
It's also very close to what we're doing now. When there's an accident and you can't ask the driver for why they took this action or that action, It's an expert observing what happened that gives a justification, speculation on why. That's a speculation.
But this is a good point to amplify because in another aspect of the explainable AI labs work, there's a subset of us that have been working on legal reasoning for a long time. And there's an intersection just because of the question you asked. So I work with my European colleagues who are judges and lawyers, academics. Maybe the simplest way to point out a connection is to note that last fall, the Mercedes group announced that in all of their future deployment of any level of automated driving, they will assume responsibility for all actions with no questions asked. So there'll be nothing like the Uber case that's still under challenge in the US, for example, right? So your question is very interesting with relationship to GDPR, because if the manufacturers do their accounting and risk analysis from insurance and say, we sell more automated driving cars because we claim that we will take responsibility. And it really changes the forensic analysis, like the accidents. So the US and the European Union are in stark contrast that way. Not a surprise, right?
Yeah, I think that the thing that is tripping me here, for
Yeah.
example, is just like, let's say that the reward function that you actually train your car is that +1 every time that you hit a dog. And everything else that involves driving a car safely. So now what happens is that the first time that you see a dog, let's imagine that you don't see dogs often on the street, and then you hit the dog. There is no way that the system on the right is going to be able to say like, well, you're actually hitting the dog because your AI system is incentivized to hit the dog. You'll come up with an explanation of like, I don't know, the dog was in front, it didn't see the dog. So it's like, there is this fundamental disconnect between
there's this very subtle threshold that most of the people I talk to miss, and it's as follows, is that note that there is no possibility, at least currently, of producing visual question answering on scenes synthesized in context for autonomous driving to be real time and control things. So that's the first thing. Most of the initial value of this kind of explanatory system is debugging, not in analyzing already confirmed to be within a threshold of safety. So the threshold of safety requirements are much lower in the fragmented jurisdictions in the US, but in Germany, which we know pretty well, is the German regulators want to be able to confirm that the number of scenarios correctly explained and produced reaches some safety threshold, and maybe dogs are in there or not. In Arizona, no. In Germany, yes, for example. But the question is valid, but it's about the threshold of deployment versus the framework for debugging, which you raised earlier, Miles. So that's important. Sorry.
Yeah,
Go ahead.
and yeah, this is kind of high level the graphical description of our framework. And yeah, now let's talk about more technical. So in first part, we collect data with reinforcement learning. So I use deep deterministic forward gradient for controlling self-driving cars' actions. DDPG is kind of a continuous action space reinforcement learning algorithm, and it has kind of 4 functional approximators, which are actor network, target actor network, critic network, and then target critic network. Kind of this kind of target kind of networks helps to improve learning ability of DDPG. And another thing is that DDPG also use experience replay memory, and that makes it kind of a computational efficient approach for self-driving problems as well. So we trained DDPG agent in Town 1 and 2 on Carla simulator. So Carla is a simulator for autonomous driving research with kind of advanced kind of functionalities. Town 1 and Town 2, they have kind of straight lanes, left and right turns, T-junctions, traffic lights, speed signs, and several stationary objects around the curves. So this is an aerial view of Town 1 and the Town 2 on Carla simulator. This is kind of reward shaping and state space representation, which I have adopted from Perez et al. 2022. So basically, reward is divided in this way. If there is a kind of road departure or collision, we give this much reward to it. And if it drives inside the lane with some yaw angle, then reward is shaped in this way. And finally, if it's kind of moving in the middle of lane, in the direction of the lane, we give it kind of highest reward. And then our state space is represented using velocity, lateral distance to the kind of lane, and in terms of yaw angle. So here I have shown kind of state space representation for an autonomous car. And here is it's kind of learning curve of DDPG over 500 episodes, and here is we have average reward. And I will now show you some short video about how.
Just in the back, you might want to one slide back. Just forward, just that graph. When you say you talk about episodes and you talk about average reward, what is the input? What is being learned? Is it a video? Is it a sense environment?
Well, sensory environment is kind of, let us say, learned. So as an autonomous car, let us say, moves ahead, it collects reward in each step.
So it's those three parameters you
Yeah, exactly. Kind of state, action, and reward.
Yeah.
So in a state, it takes action and it collects reward. And this kind of shows average episodic reward.
No, that makes sense. I just wanted to make sure that it was clear what the input was to be able to judge the reward.
Yeah, sure. Yeah. And here's kind of some short video how that driving looks like. So you see, and it's kind of a field of view from an autonomous car's camera. Sorry?
I saw doctors.
It's not
Yeah,
in the
in the large language model, that would be known as hallucination.
And in this experiment, in town 1, town 2, you don't have other cars.
No, I don't have another car. Yeah, I will specify it. Yeah, actually,
No other moving objects.
yeah, this kind of, because this is kind of preliminary experiment, here an autonomous car only interact with stationary environment. There is no moving objects, dynamic objects around, and I will also talk about these limitations in upcoming slides. Yeah, this is so how that driving video looks like. And so this was the first part, reinforcement data collection with reinforcement learning. Then the second part is visual question answering, which is our explanatory approach to kind of interpret RL agent's decision in a post-hoc manner. So what's VQA? So basically VQA is a task in the intersection of NLP and the computer vision, which produce an answer to a text-based question about an image. So basically for a VQA framework, we have two inputs, an image and a natural language-based question. And by this way, our VQA system predicts an answer to that question about the provided image. And if I repeat the example again, here we have an image, right? Turning, for example, driving scene with a turn right. And if we ask question, why is the car turning to the right? And the VQA system predicts kind of possible answers for such question about this image.
What is true correct answer?
True correct answer. So we have true correct answer is kind of turn right here because the road is bending to the right. So we already know that. So it's kind of supervised learning approach.
Again, how do you know that? Because you wrote the algorithms.
Yeah, in the video, for example, I see that, okay, an autonomous car turns right. So there is a kind of label for that. Okay, in this kind of scenario.
Now I saw the same car doing this.
Your answer is at the beginning of this talk where you said all of the images were annotated by hand.
Fine,
So
but
Russ always asks about ground truth. That's where
I
it comes
know,
from.
but ground truthing a human induced is not what I want. Thank you, thank you. That's human induced.
Yeah.
But that's the basis by which you select the quote correct answer.
Which human, we'll talk about later.
Sorry, I just had something to add to that. Like, I get in this example, you would turn right because the road is bending to the right. But if you're at something like, I don't know, like four-way intersection, there's multiple ways you could go. Sort of, is that decided just by the action that the car took?
Yeah, actually, yeah. I mean, I will talk about this in the upcoming slides as well. So basically, we define 5 specific action categories here. These are kind of go straight, turn left, turn right, turn left and right in T-junctions. We don't consider 4-way intersection so far, but we have T-junction. So because this is kind of preliminary experiment, I mean, it is not, let us say, very advanced. I mean, it does not kind of, how to say, it does not enclose all possible traffic conditions. We just focus on 5 specific action categories, which are again turn left, turn right, go straight, and the turn left and right in T-junctions. I don't consider 4-way intersection so far, but it's our next work, let us say.
You could similarly ask, why didn't you turn right? Right.
Sorry?
You could similarly ask, why didn't you turn right? So if you have a 4-way stop, the learned policy to date would say, pick the top action, turn right, but you could say, why didn't you turn left? And you could still expect the mechanism to provide some kind of explanation.
Yeah, that's also possible. Yeah, because we have kind of, I will show. So we have kind of 5 annotations so far. That's why it's a little bit limited. And why do we use visual question answering? What's the motivation behind this? So when we use an autonomous car, or when we are kind of use general cars, we always kind of judge traffic situations, right? For example, we say, okay, what will other car do in front of me? What will happen, for example, to the traffic light after 5 seconds, and so on. And if we know answers to such kind of questions, it helps us a kind of more reliable trip and more safe trip ahead. And that's why we can say that question answering mechanism can help us also justify self-driving vehicles action decisions. So this is our motivation to use VQA system as an explanatory approach.
Implicit in this is the philosophical assumption that humans are involved in navigation somehow at some level. And that confirmation of safety is done by an external agent wanting to do the forensic analysis.
Yes.
Like your explanatory system could also be used by the German Transportation Division to analyze a Tesla accident, for example.
Yeah, exactly. I will also give it in upcoming slide as well in practical use case of such kind of mechanism. And so once we have kind of video generated by an RL agent on Carla, then we convert this video to image sequences in standard rate, which is kind of 30 frames per second. Then we define 5 action categories as per your question, which are kind of go straight, turn left, turn right, turn left at T-junction, and the turn right at T-junction. So we kind of just deal with such kind of actions. Then each image frame which has been obtained from video is annotated by us using kind of textual question and answer. So if it is kind of go straight action, then the relevant question for that, why is the car going straight? And the relevant answer is because the road is clear. Because we already know the road conditions, because we know that there is no kind of aerodynamic objects here. So we know these answers before. That's why it's kind of a supervised learning kind of approach. So these are kind of our defined kind of question and answer pairs for these action categories. And how data annotation is done. So we use 250 image frames as a training data, which is obtained from Town 1. And we fine-tune the original VQA framework, which has been developed by Antal et al. In 2015. This original VQA framework has been pre-trained on MS-COCO image. So MS-COCO is kind of large-scale image collection, which has been developed in 2014. And it's also kind of one of the benchmark data sets. And in these 250 image frames, each of 5 action categories has 50 images. So 250 is equal to 50 times 5. And for testing kind of or VQA, let us say, framework, we use a collection of 100 images from Town 1 and the Town 2. And again, we also have kind of same number of images for each action category, which is kind of 20. And here again, Town 1 and Town 2 on color simulator, we use training images from Town 1 to fine-tune the original VQA framework. then we use a collection of 100 images from town 1 and town 2 to kind of to evaluate or develop a VQA framework. So, any questions on this?
How do you come up with the question that you attach to that image?
The question we define ourselves. For example, this is okay. I have a video. I see that okay. In this video, in this segment, an autonomous car turns right. So I know that there is not an obstacle there. So based on my inspection of that video, I see that okay, for such kind of driving scene, an appropriate question would be, why is the car turning to the right? And an appropriate answer for that would be because the road is clear. So I define by myself. I mean, I define those kind of.
For the same image, you can define different appropriate questions too.
Yeah, you can define other questions as well. But this is kind of one kind of question and answer pairs that I defined, which reflects semantics of that driving scene.
And if there is such a thing as a simple LLM, you could use it as an interface to generate research.
Yeah, exactly. Yeah. So it's kind of human annotation. That's why I mean there could be several shapes for this in this. Yeah.
I mean, I like the question that Randy asked before.
Mhm.
Instead of saying why did you turn right, you can ask why didn't you turn left?
The negative.
Negation.
Yeah, that's true. Yeah, this also needs to be addressed. Yeah, I will also talk about this.
Those questions in general, we see a lot in the legal reasoning domain for 10 years. And they reveal how difficult it is to distinguish between a positive and a negative statement. We have some tests on all of the chat series and a few other LLMs that show they're absolutely abysmal at recognizing negation in
And
sentences.
the expected
But that's
answer.
not a surprise.
The
Right?
expected answer can fit.
Yeah, exactly right. Yeah, the expected answer isn't necessarily what you might expect.
The fact that it's no objective measure that it's.
Well, in fact, I think that's the trajectory, that there isn't an objective measure. Yeah.
So for each question, are there multiple answers or is there just one answer for each question?
There's one concrete answer.
One correct answer.
One correct answer, but there are 1,000 kind of candidate answers. So 1,000 candidate answers, I will also explain it in upcoming slides. So 1,000 candidate answers kind of contain description from MS Coco image and the 5 kind of answers that we add to kind of that MS Coco descriptions. So given a question, given an image, or VQA framework should predict correct answer out of this 1,000, 1K kind of candidate answers.
So be cautious. This isn't about the design of a system that's engineered to do what you're asking the question about. It's an experiment to show whether or not and where the problems are in combining language and vision to be able to debug the policies created for driving. And the reason that's different, you can take this trajectory. Suppose you do stick a simple LLM in there to help with the human interface. Hallucinations are not allowed. Right? They compromise safety. So no regulator would allow that to happen. And that's why we're trying to reconstruct this bottom up with these kinds of framework and experiments.
Okay.
That helps.
Yeah, but yeah.
So it's not just learning the relationship between the question of why is it going great, always answered, because the road is clear.
Yeah, the relationship is almost like much richer for sure.
Yeah.
But this is to demonstrate how the framework would interact and in fact solicit these kinds of questions.
Yeah, basically, I mean, there could be, possible questions and answers for one scenario. But because this is the first empirical study that explains autonomous driving actions, visual question answering, so we just present our initial approach. But still, there are several limitations that we should overcome. But yeah, for now, if we have one image, if we ask one question, we expect one correct answer for that question.
So one of the pictures, the picture which showed the car turning right, and the question was, why did the car go straight?
Yeah,
We'll do that.
that's a good question. That's also I will talk about. Yeah.
Well, that's an error in the mapping, right?
Well.
Yeah, it's also it can be it can be intentional. It can also be kind of, for example, let us say visually impaired
It's a
person.
hallucination, it's not real.
It's a question about an action that didn't take place.
Right.
Basically.
Well,
Yeah.
Well, the number of actions that didn't take place is a very large.
But maybe,
decline.
but at that moment, it was about to turn right, but it was going straight at that moment. I'm sorry.
Yeah, I mean, that's a really nice question, Ross. Actually, yeah, I will explain. So basically, there could be two cases. One could be adversarial question, for example.
Yes.
An autonomous car turns right, but you would like to test your autonomous car. You say, okay, why are you going straight? So this is kind of adversarial question asked by a passenger to the, let's say, to the car, right?
Or
And
by a
another thing is,
regulator using a system to interrogate the system.
Or by, at that moment, it's going straight, because it turned right, then went straight at that moment. It's not right.
So- so yeah, I mean, that's why, I mean, there could always be some maybe bias in training data, for example. We should be careful when we annotate the data. This is okay. If the car is about to, for example, turn right, if there's a yaw angle, so probably we can say, okay, turn right, action starts, and we can annotate it accordingly.
So I have a similar skepticism, but I think it arises because of the, if you like, the discretization of the sensor space. How many image frames do we need to make the decision? Did we get it right, Because you're talking about the threshold, about whether the question even makes sense at that time. And I don't know how to answer that question. My computer vision
Well, the
friends don't
correct
know.
answer might be, that's the one question to ask.
Yeah,
The answer is,
exactly. Yeah, that's kind of generic problem with
Yeah.
VQA systems. For example, you try to kind of fool your VQA system by asking wrong question to see how it will behave. But this kind of a hallucination issue with VQA frameworks in general.
stop interrupting the question.
No
Sorry.
problem. No problem.
In the interactive debugging, that's one of the things that Shahin and I have talked about is how do you, or when do you expand the segment, the sensor fuse network? Do you expand it because you missed the threshold of that question you just asked, for example? So it's a whole other dimension of debuggability. Computer vision people don't consider it so much because their classification of the behavior in the video has different motivation. Anyway.
And here are some technical details about our VQA network, how it's composed. So it has two neural networks, multi-layer feed-forward network, which has two hidden layers, 1,000 hidden units, and tangent activation function. And we applied dropout regularization in each layer. And then we have LSTM, which is followed by softmax layer, which is employed to produce an answer for the asked question about the driving scene. And in image encoding part, we use pretend with G19 architecture, and which constitute 4096 dimensional vector. Then we do some linear transformation and then make it kind of 1024 dimensional. Then question encoder, the LSTM model for this also has two hidden layers, 512 hidden units, and it's also 1024 dimensional vector. The reason is that we would like to kind of to combine these two vectors together so that they kind of provide a bit provide good joint semantics, and eventually we multiply these vectors, and the multiplied vector is cast to fully connector layer of the VQA pipeline. So this is kind of image vector, this is kind of question vector, and the eventual vector that's passed to the fully connected layer is a resultant vector VR. And yeah, so this goes to your question. For example, what are kind of some maybe possible answers? So in MS COCO image, there are 1,000 possible answers. For example, if you ask a question about an image, there is possible 1,000 answers. And we also add our 5 annotated answers to that original answer set. So the expectation is that, given that we have fine-tuned the original VQA framework with our traffic-related image, and when we ask question or kind of VQA framework, will correctly pick up the correct answer for the asked question. So question, image, we have 1K candidate answer, and for the asked question, correct answer should be picked up by our VQA framework.
And that's why in the example that you showed us before, one of the answers was orange. Orange has nothing to do.
Yeah, exactly. Yeah. So those examples come from MS Coco in the original dataset, and those 5 answers, for example, because the road is clear, because, for example, the road is bending to the right, and so on. And here is again our graphical description of our overall framework. As you can see, image, we have a question, we have kind of protein in the VGG here, then we ask this question, and we have answer set, which is 1K, and the correct answer with kind of highest softmax probability score is selected, and it becomes, for example, because the road is clear. Right. To recap so far, we used deep reinforcement learning to control an autonomous car, and we collected driving video from here. Then we converted this recorded video to image sequences at a standard rate. Then we annotated each image frame with relevant question answer pair. And our VQA framework tries to predict correct answer to ask a question about an action in the driving scene. An experimental evaluation, as we previously said, 200 images from Pound 1 was used for fine-tuning the original VQA framework. And then we also used 100 frames, which has been collected from Town 1 and Town 2 for testing purposes. And because we have kind of ground truth label for the ask good question about an image, we kind of match them, and we use kind of accuracy as an evaluation method. For example, if we see that answer with highest probability, softmax probability score has been predicted by VQA, if it matches to our ground truth label, then it is correct, otherwise incorrect. And based on our experimental results, our VQA system kind of found, let's say, correct prediction for all kind of actions except turn left. And interestingly, for turn left actions, it kind of recognizes these actions as turn right. So I will give an example the next slide, so you will understand it better. So let us say this one, first image. It is about going straight, right? So if you ask a question, why is a car going straight? These are top 5 predictions made by our VQA network. And the highest softmax probability score is assigned to because the road is clear. This kind of high number, right? 0.99, which is almost true. But here, for example, if you ask why is the car turning to the left, the correct answer was found in the second, let us say, second answer, because the road is bending to the left. And interestingly, VQA framework predicted the kind of the most possible correct answer as because the road is bending to the right. And in other cases, it predicted correctly as well. But for turn left actions, VQA framework recognized those as kind of turn right. And based on my analysis, I feel like this could be due to some ambiguity in the tested driving frames, or the shape of curves in the scene, or maybe some possible bias in my training data. So this could be something, for example, engineering problem. For example, when I do annotation, possibly I did not select those images very carefully. I mean, I tried to select carefully, but somehow it seems that the VQA system did not recognize them well. So yeah, with these current results, we had 80% accuracy. And what are some limitations? And now we will talk about limitations. Our training and testing data set is small in size, of course. So 250 images for training and 100 images for testing, it's not enough. Basically, I would say it would be better if we had at least maybe 5K at least. And here, an autonomous car only interacts with stationary environment and explains actions associated with such kind of interactions. And how such kind of framework can be used in real autonomous cars? I would say there are at least 2 cases. First of all, it can help passengers on board to monitor driving safety by judging the vehicle's decision. Let us say you are a passenger on board, an autonomous car makes a specific action, let's say right turn, and you ask, hey car, why are you turning to the right? And it can provide you an answer because, for example, the road is bending to the right. So it can instill some trust for you, right? So you make sure that, okay, autonomous car makes a correct action, and it also understands that it does correct actions. And also, the second use case is kind of use such kind of framework in forensic analysis. Let us say we can use a number of action, question, answer triplets in forensic analysis in accident investigations with self-driving vehicles. And if we use such kind of log data, we can understand, for example, why an autonomous car made a specific decision, in particular, in that, crash moment, just before it was involved in an accident. So such kind of framework kind of has at least two benefits, let us say, for real autonomous cars. And what are some possible next steps with this framework? As Marlo said, for example, we can provide VQA-based explanations in real time and intrinsic data. So our current framework explains autonomous car actions in a post hoc manner. And this is problematic in explainable AI research as well. Sometimes post hoc explanations may not reflect model's actual prediction. So that's why we, of course, favor intrinsic explanations provided in real-time manner, also reflecting agents' actual decisions. So this is one next step that I will work on, kind of developing real-time intrinsic explanations. And I will also kind of say, and this goes to Russ's question, for example, investigating and preventing potential hallucination and hallucinations and adversarial cases with VQA. For example, as Russ said, for example, an autonomous car turns right, but as a passenger, you ask, hey car, why are you going straight? So you may intentionally try to fool an autonomous car decision, or there may be some visually impaired people, maybe they may not see driving scene incorrectly. That's why they unintentionally ask maybe a wrong question about about the driving scene. So these are some open problems in VQA we also need to investigate. And this is the example that I gave. Yeah, and to conclude, I presented the first empirical study on explaining autonomous driving actions with a visual question answering approach. And based on the results, we can say that VQA mechanism may have a potential to generate intelligible explanations for autonomous driving actions. And having an interpretable intelligent driving system can help us improve safety and the transparency of autonomous driving technology. That's it. Thank you very much. Yeah.
I have two questions that I haven't asked you before.
Sure.
One is
changed the answer.
Yeah, they changed it. One has to do with labeling the data. So we have the human in the loop here to label this, but the system has learned using RL to drive within town 1 and town 2. Can we use the policy that we learned while driving to actually label those images instead of the humans?
Yeah, that's actually a good question. I guess it is something desirable, but also very challenging.
Because the human is speculating.
Yeah.
The car decided to turn because this.
Yes,
It's an interpretation from the user looking at the image.
Yeah.
But the policy,
Yeah.
that's what it was.
Well, in fact, you can generalize that. The policy is largely just guiding data generation in that way, right? So you could accumulate in the simulator, you could accumulate a whole bunch of different policies making selections in the context of town 1 or 2 or any simulator, and use that to be able to use that as already annotated data set in this situation.
Interpret the image.
Yeah, exactly, yeah. So I think you could do that and expand the database. Then the same framework is used to debug and confirm. You could then take 20,000 different navigations of town 1 and town 2 from 20,000 different cars, Eagle car software, and analyze which were the safest, for example, right, using this thing. So I think that's a good idea. That's one trajectory, and that's the one the insurers and the regulators are interested in, is what mechanism can they semi-automate for a controller to be able to say, it's okay to let it out on the road, let it loose on the road. And it won't run Lily over when he's eating his lunch.
I'll ask the second question later. I'll ask.
Oh, yeah, I have a question. So the question is your explanation generation model explainable by itself? And if it's not explainable, is that a problem?
Good question.
Ah, good question. Yeah, well, our architecture by itself is black box, for example, that VGG19 architecture with the CA, but its end result itself is explainable. So we rely on explanation of black box model. So, but yeah, to answer your question, model itself, model by itself is black box, the VGG architecture that, for example, deals with kind of image part, convolution parts.
And my answer to Ozma's question might be the principal description of how the explanations are produced, because you could say the explanation to any one question is the majority explanation for the 20,000 car data, not relying on the black box engineering of finding those thresholds, for example. So I think that's an important question. And it's one that I drive people crazy with, just your answer about, is the explanation system explainable?
Yeah.
So it's always the right question to ask.
Yeah, and also, do you feed the explanation, the generated explanation in your final prediction, or you just predict them as two heads, prediction heads? So on the one side, you predict the final answer, on the other side, you predict the explanation.
No, I don't feed actually my explanation to neural network. I just feed kind of question and image. So based on, for example, how that image is, the model tries to predict correct answer. So, but then I don't kind of feed answer part to model itself.
Yeah. Then, given the scene or given the input, your explanation and your prediction, the vehicles are condition independent. So, given the scene,
Given the
In this sequential model, they are, yes.
So, given the scenario, given the input, your explanation and your final prediction are condition independent.
Independent.
Then, what's the point for the explanation? They're condition independent.
Well, the point is about, this is kind of like preliminary development of being able to generate explanations. Back to Marlowe's question was that I answered there, is to say, we would want that loop back. Yes.
Okay.
Yeah, because you want, at the very least, we want to characterize the measure of correct explanations, like in the 20,000 car data generation example, to have an impact on whatever learning mechanism is in place. If it's reinforcement learning, we want the feedback of the explanation to affect the reward function at that point, for example. But so that's this version of the answer to your important question. Yeah.
In the example you gave, when the car was turning right, why you turning right, you gave answers like orange or customer straight. If I didn't see the scene, I had those 5 options. Why is the car turning right? The answer, because the road's turning right. I would choose that, even if I didn't see this image. How important was the image? It didn't even make a difference.
No, I mean, model sees image before, for example.
But if I didn't see the image, you told me that there's no hallucinating question. The question is, why is the car turning right? And you gave 5 options. Because the road's going straight, but it's turning left, orange, can, or because the road's turning right. I don't see the image. I'm going to guess the road's turning right. How can the image make a difference?
The image is evidence for making the choice, though. No random choice of those 5 things makes any sense. It wouldn't be allowed. And it's not part of the architecture.
So I understand what you want to say. So yeah,
If I close my eyes for the question, I got those 5 options. I would
If you close your eyes, you get what you deserve.
Yeah, for example, I understand your question. So your question may be related, for example, whether those image encoders and textual encoders actually really contribute to VQA framework, right?
Give them a here's a question.
Mhm.
If you don't get the law, if you don't get the hallucinating questions, the question I asked about roads going straight. If the only time I ask a question, why are you turning right? And it only occurs when the road's curving right.
Huh?
It's really easy to answer. It's not orange and it's not brown or green or can because the road's curving right.
No, but we expect that, I mean, the logic is that, you know, an end user, let us say passenger on board, they first will kind of look at the driving scene, and based on this scene, they ask questions. That's why in our VQA framework, we have two vectors, image vectors and textual question in natural language. So we fuse them together so that they make joint representation. And our VQA network eventually makes a decision based on contribution of these two vectors.
But in terms of the answer to the question, and those are the options. If the only time you ask me a question, why are you turning right? So the word goes curving right. You don't ask me whether it's straight. I can just give the answer.
Yeah, so in other words, do you have cases where you asked, why is the car turning right? And the answer was, because there's an obstacle in front of me.
That never happened.
Does it happen in your data set?
In my data set, no. There is no, I mean,
So that's the point that Russ, thank you.
You're really easy. You're gonna ignore the image and look at the question and pick the answer. The only one answer.
yeah, I mean, no, I mean, I haven't considered this case because this it's a preliminary study. I haven't kind of performed all the tests, for example, dealing with obstacles or etc. But yeah, this is just focused on 5 specific action categories. So I know that there is an obstacle in front of the car.
That never happened.
Yeah, it never happened. Yeah, it never happened.
Would it simply be appropriate to say that scenario isn't allowed because the actions are a function of the sensor?
Again, for explanation. Another, again, if the issue is doing the explanation, as soon as I heard the question, I can give you the only correct answer. It's meaningful.
Okay, now I understand. It's quality of explanation that.
I mean, also, generally, if I ask a question, why did you right? The answer is because I'm trying to get to the store. When right.
So like an LLM, you can ask for an explanation for anything, but that doesn't mean it's correct, right?
Well, it might be correct, but it's different layers.
Yeah.
I would ask, why are you treating right? And the answer, I want to see a tree over there. Because I'm visiting my mother.
So to paraphrase what Russ is asking, imagine I have another experiment. I remove all the images.
Yeah.
And I use exactly the same data without the images, and I use another classifier. Would you get the same kind of accuracy?
Get better accuracy. I would never say because we're screwed. The question, why is the car turning left? I would never give the answer.
So that's a good statement of saying that the accuracy in that case is actually irrelevant to the problem.
Yeah.
I can make perfect predictions about something given the original data, is if I just turn off the imaging, right? Then you're focusing on accuracy of this impoverished representation. But that's the wrong way to think about it as far as I can think.
Because in my case, why are you turning right? Because the steering wheel's broken. I'm trying to go straight, but the car's veering right anyway.
Yeah.
That's more common thing.
Yeah, I understand. I mean, is it possible? Is this another way of, for example, you don't leverage any image, but you just said, okay, you ask a question and you ask a question on the system, and it should kind of provide just textual information. But we expect that, you know, when someone asks a question, they first judge driving scene. They look at driving scene, and based on what they have observed, they ask relevant question and tries to answer in such way. But it is another possible way that, I mean, as Russ suggested, yeah, maybe there is no need maybe for driving scene, but I guess having driving scene is important because based on the driving scene, usually we ask questions. For example, we humans, when we ask questions about everyday life, we observe some environment, we observe some scene, and based on this scene, we ask a question, right?
That joins the question that Lily asked. If you had an explanation on the explanation, how did you come up with that explanation?
Yeah.
Then you would know if it's coming from the image vector,
Yeah.
or it's coming from the question vector.
Exactly. So that's why I was saying that. So we cannot we don't exactly know, for example, how much each encoder contributes to prediction actually.
That would be interesting to know.
Exactly. I mean, so currently I have seen that in VQA research, people have done it in different way. For example, some multiplies those image encoder and the text encoder, some just maybe concatenates them, right? So it's difficult to know which vector contributes more to
throw this framework over the whole set of questions. Is that the quality of an explanation can be tested by impoverishing some aspect of the explanation generation. So in Russ's cases, if you throw all the video away, it's a pretty dumb idea, but it will impoverish the explanation because it won't make any sense anymore, right? Because it's not about the video.
Yeah.
But if you enrich the video, for example, with moving objects, then it becomes more interesting and more subtle. And then the explanation would require attention to the meta view that Lily questioned.
I think sort of the best approach would be if there's multiple correct or multiple valid answers for each question, because then you would have to use the image to, discern between what the correct answer is.
Yeah, definitely. I mean, yeah, this is kind of definitely kind of one of good next steps.
Just reinvented abductive reasoning, first documented in 1900. Thank you.
I mean, yeah, definitely. I mean, we can definitely generate multiple explanations on a driving scene. For example, it can give different or descriptive temporal information about driving scene. But yeah, because this is kind of a preliminary version of the framework, I tried to kind of to describe it. Also, actually, what Russ said, it was also kind of asked by one of the survey reviewers in my paper. When I received the decision on this paper, one of the reviewers said that, okay, how do we know that which of image encoders, for example, contributed more to,
Yes.
maybe you even don't need image, maybe you just need to ask a question, but it is an open problem in VQA research. So people do it in different way. For example, some do concatenation of this vector, some do multiplication, some subtraction. But I just follow what the recommendation from the original approach. They said that usually, for example, multiplying those two encoders leads to better joint representation of image.
But when you take VR, it's equal to the V image and V.
Yeah.
Multiplication.
If you say VR is just the image only, and then VR is only the VQ only. So each time you inhibit one of them, instead of multiplying, and then you see if the result has an impact. I mean, there's an impact on the result.
Yeah,
I can tell you whether
You
it's
could
learning
do-
from the image or.
You could do in the visual space,
Yeah,
the same
that's
thing you
true.
do in the language space. So you could think about, so the creation of text fragments as rationales that you could train on and produce explanations. You do the same thing in the visual space and say, oh, this visual space captured with these simulations or in real camera sensor fusion are at a level of resolution that's inappropriate to find the dog, for example, right? And so you can say then, you can say that your hypothesis is what resolution is required to find the dog and how do I refine the data? There's another question.
There's a question there.
Yeah.
So I try to we mentioned that you have a causal method, right? But we all know that in classification problems, it's important to do data validity between train or test validity. But based on your example here, can you show me an example of the models you produce, for example, the orange option or green option in your candidates? Like if your model only supposed to produce the 5 annotated result that you added to the classifier, why bother to have that extra assorted different? So in your example here, we can see that in the second case, we have a car, right?
Yeah.
In your option, what would be the case that the model should output car as the correct option?
Yeah, actually, when we try to predict results for the 1K answer set or model kind of assigns probability score for each of 1K answer set.
But yeah, why we bother with 1K? They are not correct answer overall.
Well, because we would like to test all alternatives. We would like to see, for example, what is the kind of, how to say, how our VQA system recognize this scene and predict answers. Probably what we can eliminate some of irrelevant answers, or we can select more domain-specific or scene-related answers. It could be some possible way. So I would rephrase it as, for example, instead of we have, for example, 1,000 set, which is a kind of collection of diverse, let us say, description from image, we can have this domain-specific answer set, and we select correct answer from there. This is something doable, but what we wanted to do in the initial framework is that given such kind of image frame is fed to our neural network, and we try to kind of do stress test for it. We said, okay, there are kind of several possibilities that this image can be, but what's your prediction?
But you could put millions of options, right? Because you only make 5 of those millions. So it doesn't make your model strong compared to the case that you have 1,000 more, only 5 of the options that you could choose.
So your measure of model strength is based on the quality of the annotations and the classification. Those are just.
No, I'm saying that if you only have 5 valid labels, then it's not a strong model, because you might miss some of the key things that you might want to put it in. For example, the third case, you say that there's an obstacle in the right side, but I don't see any obstacles, right?
Yeah.
So what if you just don't have enough labels for the model to pick the correct answer? You are making excuse of why they are doing this instead of you are trying to explain why they are doing it. So it might be multiple possibilities for them to make the right turn. Probably because we are doing a navigation and the destination is on your right, right?
Yeah.
But you are not having this option in your candidate. So how you can make?
I'm not sure I understand your question, but let me rephrase what I think you're asking. Is that the repertoire of labels is definitely going to affect how you measure whether the mapping from the video to the answer to the visual question is measured by some predictive accuracy or not. For sure, that's the case, right? We want to be able to elaborate at least 3 sources of vocabulary in this learn, if you think of it as a learning problem. One is to amplify the repertoire of annotations or classifications, because we know they're much more subtle. As soon as you introduce moving objects, you can imagine how the space explodes, right? Similarly, in the visual and in the sensor fusion, is the way you sample the frames is going to change too. Because if you have moving objects, then you need to be able to isolate segments of frames that you believe capture some motion so you can make predictions. Right? And then back to what I think you started talking about, the accuracy of classification based on those 2 mappings. The vocabulary of the answer is also going to have to be amplified. So I turned right because in general, I didn't know which way I was going. And I know my destination is on the right and I had a choice, for example, a much more elaborate answer. So I think that might give you some sense that don't think of this as incrementally stable engineering towards a solution. It's not. It's design of experimental framework. Say, where do you have to focus to improve, to use explanation as a component of judging the safety of the repertoire of actions, for example. Does that make better sense to you?
Yeah, I'm just not happy with there's no option for making wrong, like actual wrong selection of the answer. For example,
Well, any of them that don't correspond to the top choice is wrong, right?
I mean, relatively correct, like
Yeah.
they are still making, for example, the question is why the car is turning left, right?
Yeah.
It could be a case that the navigation tells them to turn left, or it could be the case that the left side there is something that I want to just reach, or right hand side I want to avoid something. There's some, yeah, but you're doing.
But your examples are exactly expanding the vocabulary that is fixed to be able to conduct these experiments.
Yeah.
So the control repertoire, the first place it would give you problems is in your simple reinforcement learning activities. Because then you have to define reward functions that are based on whether or not there's an advanced signal to the left, or you spilled your coffee, or the signal light is on, or you're like Russ said, your steering wheel only turns to the right, so on and so forth.
How do I know that if you explain the policy correct? Because you are not involving policy in this like explanation.
Yeah.
So
So yes,
policies are very simple.
So you're not explaining the policy, but you are explaining the trajectory instead, right?
You're explaining how the choice was made to take one of this repertoire of actions based on the representation of this.
yeah, I mean, this is what I also previously kind of pointed that I mean, this explanation is provided in a post hoc manner, so that we use an external tool to try to explain our agent's actions. But this can be problematic, as I also showed. That okay, external tool as an explanation provided by an external tool may not reflect an agent's actual decision. But that's why I said as a next step, I am trying to develop intrinsically interpretable approach, where, for example, an agent takes an action and we explain that action in real time, which reflects policy in that explanation. But yeah, this is a limitation I also touched. But yeah, that's a very good question. That I mean, explanations should eventually reflect decisions of policy. But the post hoc explanations may be problematic. So the desirable way would be to incorporate intrinsic explanations that reflects actual learned policy.
And you remember the previous question was about how do you close the loop and have visual question answering and its accuracy based on the sample of the environment you're looking at. How do you affect the change in a policy, which is really reordering of actions, like by reward? And so that's important, but this representation and the whole system can't do that yet. It's not so far designed to do that, although it makes good sense to do that. You first want to understand whether you're going to get any signal to be able to do the classification in this very impoverished environment. If that helps. I think what you're doing is leaping far ahead at how it might actually work if it was ever deployed. And it might not be, it might end up just being like a symbolic debugging tool, if you like, of taking a repertoire of actions from a simulator and using it to measure whether in a competition, which of the pieces of software were better and more safe than other ones, for example. So that's maybe a good way to think of it.
Actually, we have two more questions from Zoom. Here too. Oh, yeah, sorry. Yes. Sure.
Kind of connecting to this cycle we've been going on. I don't understand, like I can buy into this as like a baseline or a starting point towards better explanations and intrinsic, but I don't understand how the system is explaining the autonomous car situation or the AI related to it, rather than just it's making inferences about what a vehicle would have done in that situation, like why it would have turned. And that could have been driven by a human or an AI. But I don't get how the system.
Oh, in fact, I think you're right. Yeah, you could use the same thing for debugging human driving. Absolutely can. Yeah.
So basically, you could also use interface. So you say that okay, how these explanations are provided in, let's say, real autonomous cars, right? For example, autonomous car, let's say again, turn right. You are a passenger on board. You ask a question, "Hey car, why are you turning to the right?" A user interface will listen to your voice and display information because the road is turning to the right. So this can be done by a user interface which has been equipped to the car.
This is in fact a framework for research done when you don't anticipate the full spectrum of the SAE grades of autonomous driving. Is when humans are more closely involved in the loop. You want the same kind of system to say, oh, I suggest that you turn right at the next intersection, and the human says why, and you get the same kind of explanation, right? So I think you're right. Maybe that's a good way to think about many of the other questions.
Yeah,
Yeah.
it seems to be
Yeah,
there's
because
this disconnect to the actual AI model used.
Yeah,
to run the
absolutely.
autonomous vehicle.
Yeah, and I think
so
that
this-
that's
yeah.
a good thing, is that there's something smart making choices, and this is a way of debugging whether those choices are smart or not.
Yes,
Yeah.
okay.
Yeah, no, I think that's a good way to think about it. It also answers previous questions, like the ones about the repertoire of actions that you
Yeah.
classify. Because I don't know about you, but I never worry about an explanation about how my automatic braking systems in my four-wheel drive cars choose the frequency of their stepping on the brake to avoid skid. I don't care about that explanation. It's at a level of detail that I don't care about. Nonetheless, from your question, one could measure the accuracy of the explanation at the frequency of four wheels at different rates, right? Automatically determining how to brake and correlate it with an explanation that says, oh yeah, you prevented the skid or you didn't. And so, but at that level of detail as a human driver, hey, I don't care. You helped me avoid a skid. Thank you. I'm going to get on with my road trip, right? So I think that that's maybe one of the things that your question asks and forces the answer to consider is the level of detail that actually makes a valuable sense. That is, you can value it and say, this explanation is useful because. Now, if you fast forward to some of the interactions we've had with regulators, lawyers, and regulation people, in our case, mostly it's been in Germany. The regulators want to be able to have a model that they feel comfortable with telling the public something like the following. We've tested 20,000 visual driving scenarios, and this particular control feature, whether it's AI or human, is projected by evaluation of your question to be correct 96% of the time. Then they can tell the public they've done their job. But finding that right level of detail is really elusive. Right? What components to vary, like the vocabulary that Russ was asking? Well, what if we didn't have that answer and we were turning left and we couldn't answer that? That's sort of like a level of determination and detail from which you can conduct further experiments, look at explanations, see if they actually help you. And ultimately, for those from the Church of Reinforcement Learning, maybe generate a signal that adjusts the reward function that changes how the policies evolve as you continue to gather data, for example. So that's where we see this being a potential value. But right now, think of this as 1960. Somebody's just introduced you to a new algorithmic programming language called C. You're writing a whole bunch of programs, you can't debug them. So here's what we're going to do is we're going to give you a visual debugger. That is, we're going to give you a debugger of your C programs that helps you understand and give you explanations of changes in variables over state. And if those explanations are good, they'll let you debug your program. And that's a very old-fashioned idea. It seems to get lost in the modern rubric of AI and machine learning these days. Damn it, you better be able to debug things because you're never going to get them right. You're going to get them close.
Basically a driving test evaluator.
Yeah, it's another. Well, based on what you made is the connection of the AI as the driver versus the human as a driver. You can imagine this being used as humans too.
Yeah.
So, for example, I'm an old guy. In 5 years, I have to have my eyes tested in order to keep my driving license, right? And so it's exactly the same kind of thing. You can imagine a simulator which shows me different road scenarios and produces explanations of what I did in those scenarios. And the regulator or the drive test saying, sorry, without your glasses, you scored 31% safety. With your glasses, you scored 98%. So keep your glasses on when you're driving is the message, right? And that's a really nice analogy to make that connection between what kind of mechanism is inside of the box that's learned how to pick an action. Means that all of back to that Church of Reinforcement Learning. I actually don't care how you choose your reward function. There are some that are abysmal and they don't make any sense to any part of the world I know. But I want to be able to evaluate whether or not those choices in a broad category of scenarios actually can be confirmed as safe by some measure.
So yeah.
End of my lecture.
Actually, I mean, the whole idea is that, we would like to establish a concept of explaining autonomous driving actions with VQA approach.
Yeah.
So we did it in a post hoc manner, which may not be reliable, as we also kind of emphasize it. So the ideal case is that we use, for example, reinforcement learning to control decisions of an autonomous car, and we also incorporate this VQA system intrinsically in real time, such that such kind of system will reflect learned policy. So this is all kind of an ambitious goal. It's challenging, but next step I will work on. As I said, but post hoc explanations, this is kind of problematic problem in explaining AI research in general. So post hoc explanations may not always reflect decisions of model's actual prediction. That's why intrinsic explanations, which kind of reflect real-time learning policy would be kind of favorable. And this is what I will work as a next step.
Based on all of the questions I've been asked and we've tried to answer today, another way to think about this is that we know of at least three autonomous driving competitions that don't involve physical vehicles, but simulated vehicles and simulators. So there's one from the Simulator Carla group, there's one from the Huawei Open Source Smarts group, there's one from the Technical University of Munich Common Road group, all of whom run competitions to see whether programmed Eagle cars can navigate things like, for example, Town 1 and Town 2 in Carla. You can think of this as a human level calibration tool for how well each of my competitors' submissions are behaving, right? So I can debug them. So I'm going to send you 10 different Eagle car pieces of software to evaluate on your simulator. I'm going to do better than just run them on the simulator and have some arbitrarily chosen score. Instead, I'm going to interact with this kind of simulator and say, here are the reasons your submission in the competition didn't work well, and here are the scenarios it doesn't work well in, for example. And that's exactly what you anticipated when you thought about whether it's an AI or a human competing, right? So that makes good sense. And that's not different from other kinds of competitions of behavior that require navigation. Like for, I should say, probably 25 years, is the robot soccer competitions have been that way. Is the most interesting ones of them have been the ones that have been operating in a simulated environment where you can do things you can't do in a physical environment. But exactly the same thing is required. And scoring, if you like, and in this case, the scoring is done by this kind of qualitative explanation that us mere humans can read. That makes sense.
This time is up. I have two more questions from.
There's still.
Yeah, sorry. So Richard Allen, wouldn't the car's answer to why turn right be that's part of my route to get to X? Would the system only be usable if when the car changes its mind and has to react to something?
Yeah, that's
on the road?
The answer is right, except this framework doesn't have an explicit representation of a plan.
Exactly. Yeah, I mean, at
It
this
makes
point,
great
we
sense.
cannot kind of generate real-time explanations as we also specified.
In
hopefully
fact,
this
in the
answers your question.
current smarts competition of the three components of it, one is a measure of how the Eagle car's trajectory in an environment deviates from the claimed goal. How far does it deviate from the perfect trajectory to a goal? That means you need a representation for the plan to get to the goal. So that question makes sense, but it requires another level of representation. What's the next one?
Yeah, and I guess Animesh's question is also similar. For example, they said, I think this project may not be easy to provide the proper explanation why the Tesla car had an accident because of its decision. Because both RL model and the visual question answering question model are two different agents. Yes, that's true. This goes to the same topic. I mean, we don't provide explanations in real time, which reflects kind of learned policy, but rather we use VQA as a VQA in post hoc manner and try to explain decisions after they are kind of generated.
It's in fact exactly the question that some of my friends in the legal profession in Europe asked. Can you build these systems and use them to identify legal responsibility? What component of the semi-automated driving system failed, and what's the explanation for why it failed, to be able to determine risk and culpability in the court? That's why the Mercedes-Benz decision to say, it doesn't matter how an accident happened in one of our semi-autonomous cars, we promise to take full responsibility regardless of the stupidity of the driver. It isn't written that way, but that's what it says, right? So that question is good in that regard.
Yeah. So again, if you conclude, we can say that ideal state is always to provide intrinsic explanations which also reflect learning mechanism, learning policy. But this work mainly tries to establish a concept of using VQA as a tool to explain self-driving actions.
I don't know about how many people know this, but you know that almost all of the Tesla accidents are explainable in terms of impoverished computer vision, because Elon Musk has literally said, we refuse to instrument our cars with any sensor data except for visible spectrum camera. That's it.
Yeah, they don't use
So,
LiDAR.
so they don't use LiDAR, they don't use sonar, they don't use anything else.
But snow is great.
Yeah, absolutely, right? And so then you say, in that impoverished system is worse than the worst human driver, because we hear, we see. I don't know that it ever makes sense to say the road up ahead smells funny, but you know, you never know.
It's still on fire.
But in fact, because we have the technologies to merge all these modalities, it doesn't make sense to throw them away. It's like to say, oh, I can be the best one-legged pole vaulter in the world, and there are all only 3 of us. Right? It doesn't make any sense to do that impoverishing. And it's related to your question about the repertoire of actions, how you measure classification, the repertoire and the accuracy of the scenes. You're bound to miss something if you're taking a video and slicing 30 frames and say, oh, we missed the fact that in those 30 frames, that cheetah running by wasn't even seen because it's moving faster than the sample rate will show. Right? For example, there's all kinds of those kind of questions that arise. Really shows you how good humans are at this and how badly we are at it as building and designing computer-based intelligence.
Actually, I would recommend this recent paper published in NeurIPS, explainable reinforcement learning in natural language. Yeah, this is published in NeurIPS. You may take a look at it. I will also read it in detail. So basically, what they do is, they develop inherently explainable reinforcement learning in natural language. So I will take a look at it to its technical details. But this is some of the promising approach. Can we develop inherently explainable reinforcement learning in natural language?
Yes, send me that link, Ivan.
Yeah, sure. I will send it to you. So this is kind of a recent paper. So probably
the first question is, Lily, can you explain the explanations? And my guess is no, because they're probably using other models to build the language, coupling with the
in any case, probably we should incorporate some kind of tool, even if it's in real-time manner. But these are kind of some open problems, not only in autonomous driving, but also in other kind of safety critical applications as well. So that's it. Thank you very much for coming.
Good question.
For good questions. Hopefully this way to make our research more solid.
Thanks for the question.